This is lecture number 3 for chapter 13, and we have 3 concepts left to cover. The first is Avogadro's principle. This states that if you have equal volumes of gas at the same temperature and pressure, these equal volumes will have equal number of particles. So if you think about it, can the chemistry room be filled with 100 basketballs and 100 marbles? And the answer is yes, because the particles are small compared to the size of the room they're in. So even though one particle is larger than the other, they're very small compared to the room they're in. So if the particles on average are very far apart, with nothing between them, you can have the same number of particles in the room. At STP, which is standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, 1 mole, which is 6.02 times 10 to the 23rd particles of any gas, will occupy a volume of 22.4 liters. So equal volumes will have equal number of particles. So here we have 3 tanks. The first tank has carbon dioxide. The second tank has helium. And the third tank has oxygen. They each have, in this example, 5 molecules. So at equal temperature and pressure, the same volumes will have the same number of particles. The second concept we're going to look at today is a real gas versus an ideal gas. An ideal gas is non-existent. An ideal gas will always stay a gas no matter what the conditions of temperature and pressure are. Its particles could have no volume, and they could not have attractive forces for each other, and they could not be attracted to each other at all. There is no gas for which this is true, because all gas particles have volume, even though it's very small, and all gas particles have attraction for other gas particles. Because of this, real gases can be liquefied and even solidified by cooling and applying pressure. An ideal gas cannot be, but there is no such thing as an ideal gas, because all gases can be liquefied or solidified. So when will a gas be ideal? When will a gas stay a gas? And that will be at high temperature, so that the gas has a lot of energy and can move around, and low pressure, so that it has a lot of space for the particles to be apart from each other. Another question you're going to be asked is, when will a gas be non-ideal? So when will a gas deviate from ideal behavior? And this would be at low temperature and high pressure. So at low temperature, the particles come close together, not as much energy, and at high pressure, we can squeeze them together enough where they can turn to a liquid or a solid. The third concept for today is stoichiometry and gas problems. Stoichiometry, if you remember, is just taking a balanced equation and changing one of the coefficients and then seeing what that does to another coefficient. So if we're at STP, an equation also relates volumes. Remember, 1 mole of any gas occupies 22.4 liters. So here we have a relationship of 1 mole of N2 needs 3 moles of H2. Well, we can also see that's a volume, where 1 liter of N2 needs 3 liters of H2. So if we have 22.4 liters of N2, which is a mole, we need 3 times 22.4, or 67.2 liters of H2 to produce 2 times more, 44.8 liters of NH3. So all we're doing is keeping the ratio the same, but this time for volume. So what if we have 10 liters of N2? Then we would need 30 liters of H2 to produce 20 liters of NH3. So we'll do one today and the rest in class. First we balance carbon, carbon, 4 H's, 2 in front, 2 plus 2 oxygens, so there's 4 oxygens, so we put a 2 in front. Ones are understood. So now what if I have 22.4 liters of CH4 reacting? Then I will need 2 times, or 44.8 liters of O2 for the reaction to occur. So we'll do the rest in class. That's it for today. Have a great night.